Hi, my name is Abhishek Singh. I'm going to be talking about RSA crypto system today. Uh, so I'm going to structure this in the way that I've done it before. So I'll be using the PowerPoint to talk about uh, some of the basic points that I want to address, and if there is something deeper that needs to be addressed, I will use a whiteboard to explain some of those concepts in detail, or to do things like a problem or a numerical. So let's start. So what is RSA algorithm? So RSA algorithm is a type of asymmetric cryptography algorithm. So when we say an asymmetric, so asymmetric basically means nothing that this type of cryptography that we use has something called, it has two types of keys. They're called private keys and the public keys. So I know, as you can tell from the name, that private key is something that is kept with in possession of the person that creates it, or only with him, and public key is something that is shared to everyone. Uh, so if I talk a bit more about asymmetric keys, you could use an example. So for example, if I want to send some, uh, if I want to request some data, if I'm a client, for example, a browser, and so what I do is I'd send my public key to the server and I'd request some data. So the server then will encrypt this data using the client, the client, my public key, and it will send me this encrypted data. And after I get this data, I will use the private key to decrypt it. This is pretty straightforward. So this helps ensure that along the way the message is not lost, or it's not decrypted by any adversary or any attacker. This is just a basic understanding of what asymmetric cryptographic algorithms are. Uh, so RSA, it works basically on the fact that it is actually very difficult to prime factorize, or just factorize any large integer. So let me just give an example here. I will talk about this. So if you have a number, let's say that number is n. If you want to factorize it, it can have, so if you want to prime factorize it, which basically means that any number that you have, you can actually prime factorize it. So prime factorizing it means that you split it into its prime factors. So now if n was, let's say, 12, its prime factors, whether it decide to include 1 or not, it will be 1, 2 is a factor, 3 is a factor. So 3 into 4, 2 into 2, 4 into 3, yeah. So these are the only possible prime factors of 12. So this seems pretty simple to do when it's a small number, right? Now let's say you have a very large number, n, like it has multiple bits. It's a very large number. So now you're asked to factorize this. How would you do it? If you were to prime factorize this, you have to actually check for each of those numbers if it is divisible by each of them or not. And to this date, there is no algorithm known for us, a definitive algorithm that can generate all possible prime factors of any number. This is actually one of the biggest problems in computer science. It is an unsolved problem. Actually mentioned this. So this, as I mentioned, the idea that can integer factorization be solved in polynomial time on a classical computer. So some of the terms that I mentioned here, like polynomial time. Polynomial time is, as the name suggests, it works in a factor of, polynomial is nothing but it can be a multiple of x power 2 onwards to x power n. Some should be something of the form of x power n, right? So the idea is that to be able to compute all these prime factors, it is not so simple. You can't get in polynomial time. It usually takes, I think, exponential time, or yeah, I think it does take exponential time. So this makes it very difficult to factorize them. So now in RSA algorithm, we may use of the difficulty of this problem to our advantage. So now let's talk about how we will do that. So let us just start with an example. Let me refresh this. So think of a number. Okay, so suppose we take two prime numbers. Each of them are, we define them as P is 53, Q is 59. All right, so now there is two things that you have to do. You have to generate a public key and you have to generate a private key. So first, let's start off with generating the public key. So we take these two numbers here, and to generate the first part of the public key, there are two parts, by the way. To generate the first part of the public key, we generate N, which is our public key. We do that by multiplying P with Q. When we do this, we get 3127. Now, the thing to note here is this number that we've generated is a result of multiplication of two prime numbers. Okay, not two. Yeah, two prime numbers. So as I mentioned, the problem of finding factors, right? The problem becomes even more difficult if the number that you're splitting is a semi-prime. So a semi-prime is nothing but a number that can be split into exactly two primes as a product of two primes. So this becomes difficult because it is difficult to find the factors of primes itself. So when you try to compute what these values are, as the numbers get larger, it becomes very difficult. Okay, so coming back to this, what you have to remember is we take two prime numbers, multiply them, and that is our n value. So, and after this, the next thing we must do is choose a value e. All right. So now we have to be careful in choosing e. There are some constraints that we must follow. So e, three constraints on e is that one is it needs to be an integer, of course, and the other is it should not be a factor of n here. So that is the second condition. The third condition is it has to be in the range. This might take some explaining to do. Has to be in the range phi of n. Okay, so the number that you take should be in this range. So now I'll give you an overview of what this means. This function, it's called Euler's totient function. So basically, it tells you that it gives you the count of the prime number of the numbers, like from 1 to n, that n that is mentioned here from 1 to n, that are relatively prime. So what that means is the greatest common divisor of all those numbers should be equal to 1. So you have to keep a count of those numbers. So if you have, like, let's say you have phi of n is 5 here. So then in this case, if you start considering, if you take 1 and 5, what is the GCD of that? It is 1. What if you, and if you take GCD of 2 and 5, what is the GCD of 2 and 5? It's 1. So similarly, if you compare from 1 to 5 and keep taking the GCD of that with 5 itself, you will end up with 4 such numbers, and those numbers will be 1, 2, 3, and 4. Each of those, when you take a GCD with them, you'll get 1 as the answer. So to keep a count of those. So now I found four such numbers whose GCDs when taken with 5 is 1. So now the count of the function value of this becomes 4. So now, as this constraint holds here, this needs to be such a number that satisfies this as a constraint, and it should also not be a factor of n is not equal to k of n. I hope I'm doing it right. Okay, no, this should be n is not equal to k of n, k into n. So yeah, this is one condition, and next is it should be an integer. So for the convenience sake of our problem, for understanding it easier, let us consider e as something very small. So let's say e is 3 now. So next we have, so in this process of generating the public key, our next step is going to be so n that we have here, and then the next step. So our public key, finally, what you have to remember now is that consists of n and e. All right. So next step is to create the private key. So when you create the private key, again you take a product of two numbers. So this time the product of two numbers that you take should be, so this is the value that you take. That should be equal to p minus 1 into q minus 1. Okay, so this, when you compute this value that of the p and q's that we have taken, we get this in this case to be 3016. This is irrelevant. 3016. Now, to calculate private key, what we have to do? To calculate private key D, all we have to do is for some value, let's say k, you have to calculate D such that D is k multiplied by phi of this value that we have created here plus 1 divided by key, divided by e. So now we have our public key that we've generated here. I'll just mark this here. Public. I wish this was easier, but I'm using a mouse. So this public key that we have here consists of n, the value that we have calculated here, and e3. And now we have our private key value here, d. Basically, our private key value has to be d here. This is the only part that we'll be using in the end. This is just used to compute this. So d, when you plug the values of what we've taken here, this is 3016. If you add 1 and divide by e, then you get the d value as, in this case, 2011. So now all you have to do, okay, so remember these things. So now all you have to do, let me just open another one. Whiteboard is send a message, encrypt it, and decrypt it using these numbers that you have here. Okay, so now let us send a message. Simple message that we will send is going to be hi. So if you convert these letters into numbers, it is going to be 8, depending on the conversion that you want to take. It will be 8 and 9. So the encrypted data that you send now, C, is now going to be this message that you've taken, 89 to the power E mod of n. All right. So now this data, and after you compute this value, it moves as 1394. If you just, if you take 89 power 3 and take the modulus of that with the number n that we had here, 3127, then you get this value. And so what basically happens is, as a sender, instead of sending the actual message itself, you are now sending 1394, which is, nobody can ideally you shouldn't be able to guess what this message was to this person. At this point, you're sending 1394. Anybody trying to intercept is going to see this, which makes no sense to him. So yeah, after this message is now sent, we need to decrypt this data. So decrypt this, again, the decrypted data that we use, decrypted will be c to the power d mod n, as simple as that. So now D is the private key that we've generated. So as you can see here, while generating this, we were using the public key, and while decrypting, we are using the private key. Okay. So when you do this, you get your original value back. This, by the way, is done only to the user. You get your private value, you get your message value back, and the answer that you get comes out to be 8989 again. So you're able to read your message. This is finally what you've achieved here. This was a very simple example of how RSA works, and as you can see, some of the calculations may have been simple here, but if the messages that you're sending are long, and if there is some more complexity added to some of the factors that you take here, and you try and make the problem more difficult, it becomes extremely and almost impossible to crack this algorithm. So let us go back here. And the next thing, after we understood hopefully understood how RSA algorithm works with an example, is to understand why and where is it used. So I can clearly tell you that RSA that is used in multiple places. Like if we use it in applications like, as mentioned here, Bluetooth, MasterCard, many transactions that banks use, etc., etc. It's just very famous right now. So yeah, and one more thing, it's useful in protecting the user's identity when you do transactions. Helps you stay anonymous. So when ideally would you want to use, or maybe what is the advantage of RSA? So this works when if the sender and the receiver are sitting in two very vast, like geographically distant places. So if I was to sit here and in Chennai, and if I was to send a message to somebody in New York, this would be a very good algorithm to use, because now when I'm sending this signal, I'm sending it through some unknown territory, some maybe hostile territory. I don't know what kind of attacks my data can go through when it's going from Chennai to New York. So I have no idea about the hostility of the territory and how adverse it can be. So in such a case, I can use this form of encryption and to send my data across. So I know that whatever it is, even if somebody tries to find out what my data is, it's mathematically not possible for him to do it. Infeasible, you would say. Theoretically, it's probably still possible to be able to decrypt this. So I can probably be pretty relaxed and content with the form of communication that I'm using, regardless of however hostile or however weak the system of communication in terms of security is. I have done the encryption using RSA, and it is almost always going to be protected. So yeah, this was, again, the reason for this was basically the idea of being unable to factorize, and the idea of public and private key that we understood. And so now when we come, there is obviously a simple drawback with RSA. As I said, it was very good for transferring data across geographic boundaries, but the problem is that because of how complex it can be, it is actually bad from a performance perspective. So this, when you say performance perspective, it means that it is actually becoming difficult for the sender and the receiver to even perform RSA encryption. Forget about the security aspect of it. Like, to even engage in this, it takes a lot of computation power. So does that mean it is infeasible to use? Should we not use it? Of course not. There are things you can do to help you use it. So as I mentioned here, you can combine RSA encryption with something called as AES, symmetric encryption, to achieve the security that RSA provides and to give you the improved performance that AES can give you. So here it says a bit about how this is done, using generating a temporary session AES key. Some of these things may require understanding of what AES symmetric encryption is. We probably try not to get too deep into that, but what we can say is that despite RSA being a bit computationally difficult to do, computationally expensive, it is still used, and AES, combining with AES, one of the ways you can do to make it feasible to use in your daily applications, or just in different applications that you want to use. So that's it. That was all about RSA encryption. I hope whoever watches this can get a good understanding. Thank you for watching.